we can go ahead and start.
Can you see my screen? Hi, can you see my screen?
Yep.
Okay.
Great.
Okay. I'll begin.
Okay. Oh, okay. Yeah, I can introduce you. Thanks, Dheeraj, for giving this talk, and Dheeraj will talk about phase transitions for detecting latent geometry in random graphs. Please go ahead and start.
Yeah, I'll be as mentioned. I'll be talking about phase transition for detecting latent geometry in random graphs. This is joint work with my lab mate Matt Brennan and my advisor Kai Bresler. Okay. Let me first define what this whole talk is going to be about. It is going to be about random geometric graphs. Which will denote by RGG. More specifically, we'll denote it as RGG of NDP. Okay. We'll consider N to be the set of vertices, and D is the latent dimension. Okay. P is the probability of including an edge. How do we generate random graphs from this model? We first pick x1 to xn to be IID uniform over the sphere in embedded in RD, and let EIJ. Sorry, what just happened? Let EIJ be the indicator that let's say the edge I comma j belongs to the edge set of the random graph G. Then we'll write the following expression for EIJ, which defines them is equal to 1 if the distance between xi and xj is less than or equal to some tau p comma d, and 0 otherwise. Since all these points are on the sphere, we can easily convert it to a more convenient notation involving the inner products. That is, we can write it as 1 if the inner product between xi comma xj is greater than or equal to tpd, which is a quantity we will be using a lot, and 0 otherwise. The main questions we kind of ask in this is how is it different from Erdo-Shreni random graphs? Okay. In fact, we want to be more specific. That is, given n comma pn, a sequence of number of vertices and the edge inclusion probabilities for n belongs to n. The question is, how should d scale as a function of L so that the total variation distance between RGG of n dn pn comma g of n comma pn converges to 0. This is as n tends to infinity. So this basically gives us bounds on statistical testability. That is, if limit as n tends to infinity, the total variation distance between these two models converges to 0, then with a single sample, we cannot distinguish between random geometry graphs and Erdős-Rényi random graphs. And this will be the topic of our discussion today. This is not the most general form of random graphs with latent geometry. In the most general case, we pick the latent variables x1 to xn, corresponding each of them corresponding to a vertex IID from some metric space S, M, where S is some set and M is the metric. We join nodes I and j if the distance between them is less than or equal to tau. Tau is some threshold we set so that the edge inclusion probability is, let's say, p, and it is 0 otherwise. The geometry here, which we refer to, is provided by the latent metric space S, M. These metric spaces need not be like RD with Euclidean metric. It can be more funky spaces, which lead us to an example like a random intersection graph. I'll just mention this very, very briefly, and we study these objects more clearly in our paper, and we refer you to the paper for more information. Okay, how do we generate RIG? We pick x1 to xn to be IID random subsets of let's say a universe set D, and EIJ, the edge indicator, is 1 if xi intersection xj is not a null set, and 0 otherwise. How we see this is that 1 to n are people, and the set D is the set of activities that people are interested in. And suppose xi in person I involves in the activities given by the set xi. I and j know each other if they have a common activity, and that's how we construct this social network sort of graph. For more details on this, please refer to our paper.
All right, Dheeraj, there seems to be a question. I think referring to maybe a previous slide. If you can explain more what exactly P is.
Oh, P is equal to the probability that EIJ equals 1. Does that clear it up? Okay.
Yes, I think so.
Okay. Okay. So yeah, that is something we fix beforehand, and then we play around with the rest of the things like latent dimension. Okay. So we will delve deeper into RGGs. Okay. Now, we let me recall the definition real quickly again. We had x1 to xn to be IID uniform on SD minus 1. That is the sphere in RD. And EIJ is the indicator that ith and jth vertex have an edge is equal to 1 if the inner product xi comma xj is at least tp comma d, and 0 otherwise. Now, as I just mentioned, TPD is set such that P is equal to probability of EIJ greater than or EIJ equals 1, which is equal to probability of TPD is less than or equal to xi comma xj. Okay. Now we want to test this versus, we call this model RGG of NDP, and we want to test this against the Erdős-Rényi random graphs, the G of n comma p, where each edge is either included with IID with probability p, and this is the most studied form of model of random graphs. Okay. We want to compare this specifically in the total variation distance. Let me review some literature regarding this. Okay, one of the first papers on this topic was by which considers this exact problem is by Devroy and others. They consider this as a side problem in the paper, which mainly involved counting cliques in these random geometric graphs. This was in 2011. They use Berry-Esseen type CLTs to show that when D is much larger than 2 to the omega of n, then this implies TV convergence as n tends to infinity. Okay, so this is via Berry-Esseen type CLT. And Berry-Esseen type CLTs have the error rates of the order 1 over square root d for probability of certain kinds of sets, and in this case convex sets, and each graph has exponentially small probability in either model. So to be able to approximate probabilities to exponentially small in n, we need d to be at least 2 to the omega n, and that's where the bad bounds come from. This was improved upon by Bubeck and others in their 2016 paper, which showed that when d is much larger than n cube, this implies TV convergence. Okay, and they also showed that this is tight when p is a fixed constant. P is a fixed constant independent of n. Okay, that is, there is a statistical test which succeeds with probability close to 1 when d is less than or equal to n cube. With high probability when d is less than or equal to n cube. So what is this test? This test just counts the number of triangles, signed triangles in random geometric graphs compared to Erdős-Rényi random graph. To give you some intuition as to why this test might work, let me give you an exaggerated example of random geometric graph in 2 dimensions. Suppose we have x1, x2, and x3. And suppose we are given that x1 and x2 are close enough to each other so that they have an edge, and x1 and x3 are close enough so that they have an edge between them. Then by triangle inequality, x2 and x3 must also be close to each other. So there is a higher probability that there might exist an edge between these two. Okay, so what this implies is that there are larger number of triangles compared to G and P. And yeah, so the statistical test they give, which succeeds when d is much smaller than n cube in the dense case, is exactly based on this such a triangle counting, but that is centered triangles because we want to reduce the variance in the number of triangles. So, and they use the statistics to show that should give a test which succeeds with high probability. Okay. And there, what we are interested in is in how they prove the convergence in total variation distance when d is much larger than n cube. This proceeds via random matrix theory. I should also mention that the proof of this is actually also implied by a prior result of Jiang and Lee, which came out in 2015, but they did not think about the random geometric graph problem. And Bubeck et al. Came up with their proof independently of the Jiang and Lee results. Okay. So how is this total variation convergence proved, and what are the problems of extending it to other cases? Okay. So how do we prove this? We first note that if we have RGG of NDP, this can be obtained as a thresholding of a certain random matrix, that is the Wishart matrix. I've introduced a lot of notation here. Here W is a Wishart matrix with of size n by n and with d degrees of freedom. We can see by the structure of the Wishart matrix that this must actually correspond to the random geometric graph when we pick t to be the function t of x is equal to 1 of x greater than or equal to tpd. That is, we take a Wishart matrix and threshold each of its entries by tpd, and we obtain the approximately obtain the adjacency matrix of the random geometric graph. One thing where it actually differs is that Wishart matrix contains Gaussians, or the inner products of Gaussian vectors, but we are looking at distributions on the sphere. But uniform distribution on the sphere looks approximately like high dimensional Gaussian, so it shouldn't matter too much, and we can make this more rigorous. Okay, and G of n comma p can be similarly seen as a thresholding of z, where z is the GOE random, z over square root d, where z is the Gaussian orthogonal ensemble of n. That is, it is a symmetric matrix, such that is Zij is equal to Zji, and each of them is IID normally distributed. Okay. Now, to show that there is a total variation convergence between RGG and GNP, we just use the data processing inequality. That is, it is sufficient to show that total variation distance between W and Z over square root D converges to 0. And this can be done quite easily because we know the densities, and hence we can bound total variation distance via the KL divergence using Pinsker's inequality, and KL divergence can be evaluated because we know the Radon-Nikodym derivatives explicitly. So it turns out that this tends to 0 if D is much larger than n cube. Okay, this seems like a almost complete picture and everything is already known, but why do we need our work? Okay, there is a catch here. This threshold is tight only if P is, if we have dense regime, that is, if P is theta 1. In fact, it was conjectured in Bubeck et al. Paper that when P is equal to lambda over n, which is the sparse case which we are most interested in the case of random graphs, we have the threshold was conjectured to be D greater than log n cube. In fact, this is when the triangle statistic, which worked so well in the dense regime, fails, and it can be shown that all small subgraph counts also converge and are indistinguishable from those of Erdos-Renyi random graphs when D exceeds this threshold. So there is a huge gap between the dense case and the sparse case, and doing something like a data processing inequality loses a lot of information because of the thresholding, and we cannot hope to get such a bound. Okay. In fact, it was not even known that whether if Pn tends to 0, the rate becomes strictly better than n cube. That is the following question. Okay. In fact, even this question was unanswered. We in our work we answered this in the positive. Okay. In fact, we state the following main theorem. Suppose d is much larger than n log n to the 4, and d is much larger than minimum, not maximum, but minimum of n cube p log of 1 over p, comma, n to the 7 over 2 p square log n cube times square root log 1 over p. Then we have limit n tending to infinity, total variation distance between RGG of n dp, comma, g of n, comma, p is equal to 0. And so this, let's look at some of the special cases. When p is theta 1, then we recover the standard guarantees, recover the optimal guarantees. That is d larger than n cube. When p is equal to lambda over n, we get the threshold to be d much larger than n to the 3 over 2 log n to the 7 over 2, which is much better than d much larger than n cube, but it's still much worse than the conjectured bound of log n cube. Okay. Let me briefly describe our proof technique. Firstly, we apply Pinsker's inequality. And conclude that to show that total variation distance converges to 0, it is sufficient to show that the KL divergence converges to 0. And the second one is to tensorize KL divergence. Why do we need to tensorize KL? I'll get into why we need to tensorize in a bit. And the third, we'll use reverse Pinsker's inequality because we don't want to deal with too much nonlinearity. And the fourth step is to use finite definity type result. Result. This implies the threshold of d much larger than n cube p. Okay, henceforth I'll drop all the logarithmic factors, which sort of are a nuisance for clear presentation, and I'll just keep the polynomial factors. And here there are, of course, it is understood that there are logarithmic factors here. Okay, and the fifth step is to boost this bound, that is boost step 4 via a coupling bound. This gives the bound of d much larger than n to the 7 over 2 p square. Okay, and okay, let me explain why we need to do this. First of all, we saw that these random geometric graphs are horribly dependent. That is, all cycles are, if you have consider any cycle in it, it is not independent. Whether the cycle is present or not, or edges in a cycle present or not, is horribly dependent. And it is very hard to describe the probability of a given graph structure. So it would be more useful if we consider marginals or a single edge and the dependencies that arise for a single edge given the rest of the graph. That is the probability of a given edge being included given the rest of the graph. And it turns out we have the techniques to deal with such a quantity. And that's why we need to tensorize it, that is reduce our consideration from total variation distance to just considering uh, considering something over a single coordinate. And we know that total variation distance does not tensorize very nicely, but KL divergence tensorizes very nicely, by which I mean that we can reduce the KL divergence over the whole distribution to the KL divergence of a single marginal to a single marginal. And that's why we do the tensorization. But KL divergence has log terms, which is sort of unwieldy and too nonlinear. So we use reverse Pinsker inequality after we tensorize to get back to sort of a TV square kind of distance. And then rest of it is our results, where we use finite definity type results and coupling bounds to actually bound this reverse Pinsker inequality quantity. Okay, what I mean by finite definity theorem is that if we consider x to be uniform over, let's say, SD minus 1, and let's say we write x to be x1 to xd, then this result states that x1 to xn looks approximately like a Gaussian with covariance matrix in over d, when n is much less than d. That is. Okay, this is what we mean by finite definite theorem. And this approximate independence is what helps us show that, for instance, if we are given x1, x2 has an edge and x2, x3 has an edge, then the probability that x2, x1, x3 has an edge is also close to p. And that follows from this kind of approximate independence, as we will show later. Okay, and the coupling bound is hard to describe intuitively in words. I'll describe it mathematically in a bit. Okay, let me state 3 information theory lemmas, which are quite standard. The first is Pinsker's inequality. That is, suppose mu and nu are probability measures over a space omega, then TV is bounded above by square root of KL. Therefore, it is sufficient to prove that KL divergence converges to 0. In what follows, we'll take mu to be, let's say, RGG, and nu to be GNP. Okay. Now, the second one is KL tensorization. When the base measure is a product measure, like nu is Eratosthenes, which is a product measure, then the KL over the global distributions can be seen as a KL over the local distributions. That is, if mu and nu are probability measure over a product set, omega to the m, where m is a natural number, and nu is a product measure, that is a product of nu1 to nu m. In our case, this is a tensor product of m times of Bernoulli p, and omega in our case is 0, 1, which is indicator of each edge being present, and m is equal to nc2, which is the maximum number of pairs of vertices which can have an edge between them. Okay, and then we can tensorize KL as follows. That is, KL divergence between mu and nu is less than or equal to this quantity on the RHS. Let me explain the notation here. Here, G tilde E belongs to omega to the m minus 1, which is all coordinates of G other than E. What we see we see this in our context as the rest. If we have an edge 1, 2, then we consider we don't look at that whether that edge is present or not, and we look at the rest of the graph and call that G tilde E. And what this means is that G tilde E is drawn from the marginal distribution for the rest of the graph. And what is mu E of dot G tilde E? This is the probability measure of the eth coordinate GE conditional that we are given the rest of the graph, G tilde E. Okay. So this is quite easy. And then we take the expectation of this. And the base measure here is nu E. And since we don't need any conditioning here because nu is a product measure. In our case, nu E is equal to, let's say, Bernoulli of P. Okay. When we take mu to be the RGG and we define some notation here, we take QE is equal to probability that the edge E is present in the random graph given the rest of the graph. This is again a random variable, which is a function of G tilde E. And then therefore this can be written as KL of mu given nu is less than or equal to summation E equals 1 to NC2. Expectation of G tilde E goes as mu tilde E KL between Bernoulli of QE to Bernoulli of P. Okay, this is the natural quantity which arises here. Now, when we have Bernoulli's, the KL divergence can be sharply bounded, given that we know the base measure. This will call the reverse Pinsker inequality. That is, which basically shows that KL divergence behaves quadratically near its close to its base measure. That is, the KL divergence between Bernoulli Q and Bernoulli P is at most Q minus P whole square over P. So as long as P is not 0, we are fine. Okay, writing this down, we know that in the case of a random geometric graph, all edges behave similarly. So without loss of generality, we know that all of these expectations are the same. So we fix the edge E to be n minus 1 comma n without any loss of generality. And KL tensorization and reverse Pinsker inequality applied to this case show that KL divergence between RGG and G of n comma P is less than or equal to NC2 times expectation mod QE minus P squared divided by P times 1 minus P. To remove some of the nuisance aspects in the expression, we just write it as n squared over P expectation mod QE minus P whole square. Here, the expectation of GE goes as mu tilde E is assumed when we say QE. Okay, so okay, so next we see that we have completed the first step, which is tensorization, which is Pinsker, and next we tensorized, and then we looked at reverse Pinsker inequality. Now we need to use this finite definity theorem to show the first bound, and this is what we are going at now. Okay, first, what kind of finite definity theorem do we have in mind? We want to show that mod QE minus P is less than or equal to P square root of n over D with probability at least, let's say 1 minus 1 over n to the 100, when D, let's say, is much larger than n log n to the 4. Okay, so okay, let's say that we were able to show this. Let's go back to our reverse Pinsker inequality, which we got for KL divergence, and plug this in and see that we get the first bound. We saw that KL between mu to nu was less than or equal to n square over P times expectation mod QE minus P squared. Since this low probability set is very, very small as any arbitrary inverse polynomial, we can just write this as less than or equal to n square over P, writing this here, times P square times n over D, which is equal to n cube P over D. Therefore, D much larger than n cube P implies convergence. Okay. I'll spend some time proving this result. To prove this, we look at Gram-Schmidt orthonormalization. So we have already assumed that D is much larger than N. Inner products are unaffected by any rotations, even arbitrary rotations, which can depend on the points themselves, because rotations preserve inner products. So we can, without loss of generality, we can write x1 to be x1 x11 comma 0 0 0. There are d minus 1 zeros here, and x2 is equal to x21 x22 0 dot dot 0. And similarly, xn, we can write it to be xn1 xn2 dot 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 xnn 0 0 0, and there are d minus n zeros here. Okay, fun fact here is that by the fundamental properties of high dimensional sphere, the uniform measure on the high dimensional sphere is that x11 and is approximately 1. So is, let's say, xii is also approximately equal to 1 with very high probability. And xij is very small. That is, if you pick two points independently, uniformly at random from a high dimensional sphere, they are approximately orthogonal. So this implies that xij is of the order 1 over square root d. Okay. We recall that QE is equal to probability that xn comma xn minus 1 is greater than or equal to TPD given G tilde E. Okay. What does G tilde E depend on? G tilde E is nothing but thresholding of xi xj for I comma j not equal to n minus 1 comma n. So this is actually, because of the nonlinearity, this is a very hard sigma algebra to deal with. So we'll actually relax it a bit, make it finer, and include more things into it. So we won't be bounding exactly QE, but we'll be bounding a finer version of QE, that is Q naught. And it is actually, after a bit of technical effort, it is easy to show that even this by a Jensen's inequality is just sufficient to prove our bound. Is probability of xn comma xn minus 1 is greater than or equal to TPD given let's say x1 to xn minus 1 and xn1 to xn n minus 2. If we can just explicitly compute the inner products here and show that knowing all these numbers will give us the information on G tilde E, but not vice versa. And what is conspicuously missing here is xn n minus 1. Okay. So when we're given xn n minus 1, then we know that xn1 to xn n minus 1 are the first n minus 1 coordinates of xn with respect to some random orthonormal basis, which is given to us by the Gram-Schmidt orthonormalization of x1 to xn minus 1. So these coordinates must behave approximately independent. And this is the definity type result. I'll actually just wave my hand for a bit and just and leave out the rigorous proof of this. But we have an actually elegant and beautiful proof which uses a nice coupling argument to quantify what we mean by approximately independent and what we mean by definity type result. But right now I'll just wave my hand. Okay. We have an explicit expression for the inner product between xn and xn minus 1 in terms of a lot of quantities we defined here. That is, we have xn comma xn minus 1 is equal to xn minus 1 times n minus 1 n minus 1 times xn n minus 1 plus summation j equals 1 to n minus 1 x n minus 1 j, xn minus 1 j, and xn j. This is n minus 2. Okay, so we've seen that by concentration of measure phenomenon, this quantity is of the order square root n over d with high probability, by which I mean it by at least 1 minus 1 over n to the 100. And xn minus 1 and n minus 1 is approximately 1. Okay, so therefore this q naught can be written as probability that xn comma n minus 1 is greater than or equal to tpd minus o of square root n over d divided by 1 minus small o of 1 given x1 to xn minus 1 comma xn1 to xn comma n minus 2. Okay, this O of n over root d and small o of 1 are all dependent on these random variables which are conditioned here, but with high probability they are ignorable. We'll call this quantity TPD prime. Okay, that is, this is equal to probability of xn comma n minus 1 greater than or equal to TPD prime given all these random variables. Now we go back and we actually check that by definition, P is equal to probability that xn comma xn minus 1 is at least TPD. So this suggests us a natural way to bound the difference between these two. And we know that the law of xn comma xn minus 1 is independent of whatever was being conditioned. And we also know that TPD minus TPD prime is less than or equal to O of square root n over d with high probability, which is 1 minus 1 over n to the 100, where the high probability is over the what we are conditioning in the background here. Okay, so therefore q naught minus p is equal to integral TPD prime to TPD without loss of generality, assuming that TPD prime is less than TPD, psi d of t dt, where psi d is the density of xn comma n minus 1. Okay, so to bound this quantity q naught minus p, it is sufficient to bound this integral. We can actually show that this deviation is not too much when d is large enough. So this can be approximately written as psi d of TPD times mod TPD minus TPD prime. Okay, and we can show via easy calculus on the distribution on the density function that this is approximately equal to p times square root d log 1 over p, some constant, times square root n over d, which is p square root n over p square root n over d up to log factors. Okay, and yeah, p square root n over d with high probability. And this is exactly what we set out to prove in the fourth chapter, that is this finite definity type result. And this finishes the third step in our proof, which gives us the first bound, which is d much larger than n cubed times p. Okay, so now we can we continue our study here, and we realize that we can make it much better. This in the case p is when p is lambda over n, this gives us d larger than n cube n square type threshold. We can actually do better than this by adding one more step of coupling here, which I'll describe now. We had the following bound on the KL divergence between mu and nu, which was that this is less than or equal to n square over p, expectation of mod QE minus p squared. And where again, let's recall QE is equal to probability that GE equals 1 given the rest of the graph. Now we had the definity type result. I'm sorry, I don't know if D or F have to be capital. I forgot. Yeah, so definity type result that which showed that QE is minus P is less than or equal to P times square root of N over D with very large probability. Okay, so instead of just applying it to the whole expression, what we will do is we will show that KL of mu given nu is less than or equal to N squared over P times expectation of QE minus P times QE minus P, which is less than or equal to N square over P times N square root N over D, sorry, P square root P square root N over D times expectation mod QE minus P. Okay. So why did we do this? We just applied this definity type result to one of the terms instead of both the terms. Why did we do this? This because we can actually write this in as a closed form expression of total variation distance between two different measures. What are those measures? I'll describe in a bit. This is equal to n to the 5 over 2 over square root d expectation mod QE minus P. Okay, so we can actually show that expectation of mod QE minus P is equal to 2 times P times total variation distance of mu E plus, comma, mu tilde E plus and mu tilde E. Okay, what is mu tilde E? We are aware of what mu tilde E is, which is marginal distribution of G tilde E. And what is mu tilde E plus? This is the distribution. This is the law of conditional law of G tilde E given GE equals to 1. In the random geometric graph, we set the edge E to exist in the graph and look at the distribution of the rest of the graph. Okay. Now continuing on with the previous bound, we have KL between mu and nu is at most n to the 5 over 2 P over square root D times total variation distance between mu tilde E plus to mu tilde E. Now, once we have expressed this as a total variation distance between these two funky probability measures, we can use a lot of tricks associated with how we bound total variation distances typically. That is, we use coupling bound. That we suppose G tilde E is distributed as mu tilde E and G tilde E plus is distributed as mu tilde E plus over a common probability space. Okay, then TV of mu tilde E plus comma mu tilde E can be upper bounded by probability of G tilde E not equal to G tilde E plus. So coming up with a nice coupling between these two distributions is sufficient. And I'll just construct the distribution, construct the coupling I have in mind. I think we are almost out of time. So to do this quickly, how do we will use the convention that x1, let's say xn is equal to en, okay, which is a standard basis vector almost surely. This does not in any way affect the random graph if we choose the rest of them to be uniformly at random on the sphere, because we can always rotate it and without changing the structure of the graph. Okay, we take xn to be en and x1 to xn minus 1 to be IID uniform over SD minus 1. And we obtain G tilde E by thresholding the inner products between x1 to xn. Okay. And this gives us G tilde E, which is distributed as mu tilde E plus. Distributed as mu tilde E. Now, how do we generate mu tilde E plus? Now, we will keep the same x1 to xn minus 2, same as before. And we also fix xn to be equal to en almost surely, same as before. But instead of xn minus 2, we set it to be xn minus 1 plus. Okay, what is xn minus 1 plus? We will write it to be, let's say, gamma plus times en plus square root of 1 minus gamma plus square divided by square root of 1 minus xn minus 1 comma en squared times xn minus 1 minus en times xn minus 1 comma en. Okay, we use this convention where we basically take xn minus 1 where, okay, I forgot to define the notation here. Here gamma plus is distributed as xn minus 1 comma en, given that xn minus 1 comma en is greater than or equal to TPD. That is, we force set the edge between n minus 1 and n to be 1 to exist in the graph. Okay, and then we go back and reverse engineer the point xn minus 1 plus, so that this has gamma plus in the direction of en, making the edge to exist, and we rescale the perpendicular component to xn so that it is the same as it is in the same direction as xn minus 1. So this is sort of a maximal coupling. Now we need to bound probability that G tilde E is not equal to G tilde E plus. Okay. When does this event happen? Okay. This happens when for some j equals 1 to n minus 2, we have xn minus 1 comma xj is greater than or equal to TPD, and xn minus 1 plus comma xj is less than TPD, or vice versa. Via the same coupling argument and concentration of measure inequalities, we can show that xn minus 1 plus minus xn minus 1 times xj, the norm of this is less than or equal to log n over d, with high probability. High probability, I mean at least 1 minus 1 over n to the 100. Okay. So these are very close to each other, and one of them has to be above the threshold and one of them has to be below the threshold. Let's draw a picture. Okay, let's say we draw the density of the distribution of xn minus 1 comma xj, that is psi d, and the threshold is here, that is tp comma d. And okay, so one of them is below the threshold and one other is above the threshold, but the distance between them is bounded by O of log n over d. This in particular means that xn minus 1 comma xj must belong to this narrow band of width O of log n over d. And this this event can only happen when xn minus 1 comma xj belongs to this narrow band. What is the probability that the inner product between xn minus 1 and xj belongs to this narrow band? That is approximately equal to, let's say, psi d of tpd times O of log n over d, which is approximately equal to p times square root t over d up to log factors, which is p over square root d up to log factors. Now, we did this for a specific j, but we need to union bound over all j equals 1 to n minus 2. Therefore, probability of g tilde e not equal to g tilde e plus is less than or equal to np over square root d, see, up to logarithmic factors. Now we go back to our previous equation way above here, which showed this. Okay, let me copy that back down. KL between mu and nu is less than or equal to n to the 5 over 2 p over square root d times probability of g tilde e is not equal to g tilde e plus, which is less than or equal to n to the 7 over 2 p square over d. This implies that when d is larger than or equal to n to the 7 over 2 p square implies convergence, which is what we set out to prove in here. And this this proves our theorem 1. Okay, there are a lot of open questions here, as in how to prove the conjectured bound. We just proved that when p tends to 0, we can make the threshold better than n cube, but even we do believe that the threshold is sort of log n cube. There are many problems we encounter when we try to reach below when d is much smaller than n. For example, the finite definity type result does not hold because the dimension is already much smaller than the number of points. And if you pick any d points, they already form a basis, and they're not even linearly independent anymore. So it's not clear, and that is one of the bigger open problems regarding this. Thank you.
Okay, thanks, Dheeraj. So if there are any questions, you can use the Q&A or I can unmute anyone. And yeah, I guess there will also be a break going on now until 12:45, where Pravesh Kathari will tell us about recent progress in algorithmic robust statistics via the sum of squares method.